Face to face I found my pain beneath the lies and broken dreams. Lost the love I had in me, it tore me apart, fade away. I felt so lost, but I held on to what I had. For what it's worth, if you're feeling low, just know that you can, yes you can. There's life in love that you hold. Rise above and let it glow. Just know that it's never too late to make a change. Crash and burn, I found myself beneath the emptiness. Wanting more, I let it go. Holding on to love. Breaking through, I feel alive. For once in my life, I'ma live by the want to be all I can. Let the rest just crash and burn. Crash and burn. Oh wow, oh wow, let it crash and burn. This one for the person who feels alone. This one for the hero who has no home. This one for the one who live for hope. Changing better days. Pick your head up, keep on fighting, living, loving. Make your mind up. If you want it, take it, fly away, soaring high above the clouds. Hear the voices calling out. Oh, you want love. Crash and burn, I found myself beneath the emptiness. Make your mind up. Wanting more, I let it go. Holding on to love. Breaking through, I feel alive. For once in my life, I'ma live by the want to be all I can. Let the rest just crash and burn. Let the rest just crash and burn.
We get that fresh glaze on the D-roll. Pulling up, smoking haze through the back door. We get that fresh glaze on the D-roll. Pulling up, smoking haze for days. We get that fresh glaze on the D-roll. Pulling up, smoking haze through the back door. We get that fresh glaze on the D-roll. Pulling up, smoking haze through the back door.
Crash and burn. reason I point out these two guys is that Anton made sure that we have very fancy guests today, and Kirill was caring enough to provide us such a cool place.
I was
Also be busy with cooking. All of this is of course handcrafted. Fruit is grown on Kirill's garden.
that's why it's worldly.
So for today's agenda, we have two talks, both of which are 2018 Geek Out speakers. That is happening Thursday, Friday, I believe. By the way, who is attending Geek Out? Raise hands. Well, a lot. Approximately like at least a half I can see. But we made a small poll when issuing the tickets, and the number are a bit different. If we can have numbers, the next slide. Okay. So basically, quarter of respondents didn't know like what's Geek Out, and then like the half was not going to attend. But like from the audience, from the crowd, we see a whole different picture, which is of course good news, nice to hear, and I hope that after tonight's warm-up, the thoughts and the willingness to go to the conference will be even greater.
It's sold out one
sold out. Yeah,
They shouldn't
actually,
be pushing so hard.
next year. So enough of me. So we have first speaker from Google platform.
Yeah.
Yeah. Opening work from.
I'm just going to say to everyone, just a quick word. Thank you for coming. I'm the head of engineering here at Topia. Make yourself at home. There's plenty of beer and food and everything. As you see, we've just moved in last week to this fantastic new office. It's been great, but it's a bit of a blank canvas. So any suggestions welcome to what's made you work in nice offices before. Feel free to suggest stuff to myself and Kirill, and I'm sure we can work it in at some point. And I look forward to having you guys here again for future events. But two fantastic talks coming up, so I hope you enjoy. Thank you.
Yes, please welcome on stage Sara Robinson, Google Cloud Platform, machine learning stuff, and all that.
Can everyone hear? Should I turn this on? Testing. All right, cool. We're on. Hello, everyone. Just getting my computer set up. There we go. Can everybody see? Awesome. So my name is Sara Robinson, and today I'm going to tell you all about how you can do text analysis using machine learning, going from a pre-trained API where you can access a machine learning model with a single REST API request to building a custom model with your own data. So I'm a developer advocate on the Google Cloud Platform team. I'm based in New York, and this is my first time in Estonia. I just landed a couple hours ago. Still a little jet lagged, but I was in London before, so I've had a couple days. So as a developer advocate, my job is to teach external developers like all of you how to use different tools on Google Cloud Platform, and I focus on machine learning. So day to day, that involves a combination of building demos, writing code to show people what you can do with these products, giving talks at events like this, and then also writing online content like blog posts and videos. And an important part of our job is to bring feedback from the community back to the engineers who are building the product. So if any of you have used any of Google Cloud's specifically machine learning products and have feedback, things you really liked, things you didn't like, let me know and I can share that with the product team. You can find me on Twitter at srobtweets. I share almost all of my code and blog posts on there. So let's get started by talking about what is machine learning. So at a high level, machine learning involves teaching computers to recognize patterns in the same way that our brains do. So for us as humans, it's really easy for us to identify the difference between, let's say, a cat or a dog, because we've had billions of years of evolutionary experience to help us with that. To a machine, that's a much more difficult task. So machine learning involves building models that improve as they're given more examples and experience, and that they can slowly learn to generalize on examples that they haven't seen before. So if anyone remembers how you learned your first language, your first spoken language, not programming language. So your parents probably didn't give you a dictionary and a bunch of grammar books to memorize. That'd be kind of weird. Instead, you learned over time by being exposed to many different examples. So let's say you had pasta for dinner. You saw the pasta on your plate, heard your parents identify it. Maybe you identified it incorrectly a couple times and were corrected. Over time, this strengthens certain pathways in your brain. And this is roughly how machine learning works as well. So today I'm going to focus on what's called supervised learning. So this is the problems where we give our models labeled input when we train it. And we can think of almost any supervised learning problem in this way. We give our model labeled input, then our model has some algorithms that results in a prediction. Now the amount we know about how that model works under the hood is up to us and the tool we use to solve the problem and the specific type of problem that we're trying to solve. So that was a high-level explanation, but how do we actually get from input to prediction? Now I'm going to be talking about text, so natural language processing in this talk, but input could be many different things other than text. It could be the pixels in an image, it could be the audio if you're trying to do speech recognition. It could be many different types of unstructured data. In this talk I'm focusing on text. If you are coming to geek out, I'm going to talk a little bit more about, I'm going to talk about text, but also about image classification. So one example is, let's say we have the headline of this article from the New York Times, and we want to build a model that predicts that this is an article about sports. Or let's say we want to build a model that's able to tell that this is an article about baseball, a little bit more specific. Or let's say we want to do something custom and we want to build a model that's able to predict that this headline came from the New York Times. Another example of what our inputs could be is, let's say we've got a bunch of Stack Overflow posts and we want to predict the tag of these posts. So as I mentioned before, the tool you use depends on the type of machine learning problem you're solving, and I like to think of this along a spectrum. So on the left-hand side we have generic tasks, on the right-hand side we have more custom tasks. So if we're solving a generic task, someone else has already solved this before, we probably don't need to start from scratch. So we'll take this text from one of my tweets as an example. Let's say that I want to extract parts of speech from that. I want to know if it's a verb, a noun, or a pronoun for the different tokens in the sentence. This is a pretty common natural language processing task, so I don't need to start from scratch. I could if I wanted to, but I might as well make use of many of the pre-trained models out there that are great at doing exactly this. But let's say I've got a custom task that's specific to my data set. So let's take the same text, but instead of extracting parts of speech, let's say that I want my model to predict that this is a tweet about programming, and more specifically, it's a tweet about Google Cloud. Now to get these predictions out of my model, I'm going to need to give it thousands or hundreds of thousands of tweets about these different topics that I want it to extract. Because remember that the output of your model, the accuracy and quality of your model, is only going to be as good as the training data that you give it. So in this talk, I'm going to talk about how we can go from API to custom model. Since I work on Google Cloud, I'm going to be talking about our Cloud Natural Language API. There's many different APIs out there for doing natural language processing, so I encourage you to try out a bunch, see which one is best for you. And then I'm going to be talking about building a custom model with TensorFlow, which is Google's open source framework for building and training your own machine learning models. I'll get into that a bit later on. So I'll start with the API. So Cloud Natural Language is an API that lets you understand text. So you pass it text and you get a bunch of different types of analysis back. And all of the different things it can do are detailed on this slide. So the first thing it can do is it can extract key entities from text. It can also detect sentiment. It can tell us whether text is positive or negative. It can get a little bit more into the linguistic details of text. So if I wanted to do what I was talking about before, extracting parts of speech, I could do that with the analyze syntax method. And then the newest feature of this API is content classification. So you can classify your text in a bunch of different, into a bunch of different content categories. Now the great thing about using this API is as an application developer, you can access these pre-trained machine learning models without really needing to know anything about how that model works under the hood or anything about machine learning. So you can just pass it some text, get some data back. It's just a REST API, so you can access it in any language that you'd like. So it's a great way to get started with machine learning. We've got a bunch of different APIs for not just text classification, but we have image analysis, speech to text, video analysis. So if you're new to machine learning and want to get started, definitely recommend trying out an API that gives you access to a pre-trained model. Really good way to get started with machine learning. So going into a little bit more detail on what these different methods provide, the analyze syntax method gives us a lot of linguistic details on the text. So if we take this sentence as an example, the natural language API helps us understand text. This is just a visualization of all the different data we get back from the analyze syntax method. So we get the part of speech, that's what's in red. We get the role of each word in the sentence, that's the parse label in orange. So for example, API is the nominal subject, helps is the root verb. And then those arrows in green are what's called a dependency parse tree. So this tells us which words in the sentence relate to other words, which words depend on other words. Then we have the lemma. You can see here we only have one for help. So the lemma is the canonical form of the word. So for helps, the lemma would be help. And this is useful if you've got any situation where you want to count how many times a certain word was used to describe something in your application. You probably don't want to count helps and help as two separate words. You just want to use the canonical form. So then you would use the lemma. And then finally in the bottom row we get some additional morphology details on the text. And this is going to vary based on the language that you send your text to the API in. It supports a couple different languages. Unfortunately, I don't think it supports Estonian yet, but if you've got use cases for it, let me know and I can pass that along to the team. So the next method I want to talk about is content classification. So what I did here is I took the headline and the first sentence of this article from the New York Times. I sent it to the content classification endpoint. And it gives us back, in this case, just one category. So it's able to tell us that not only is this an article about sports, but more specifically, it's an article about baseball. And what's cool is the word baseball isn't actually mentioned anywhere in this text, but the API is 99% confident that it's an article about baseball. So you can get multiple categories back. In this case, we have just one. So here is some example code of calling the natural language API from Node. I do a lot of my demos in Node.js, but obviously you can call the API in any language that you'd like. We have a number of different client libraries for popular languages. So this is an example in Node. We're using the Google Cloud Node module, and then we're creating a reference to the language object. And then in this case, we're passing it the URL of a text file in Google Cloud Storage. You can also just pass it the raw text that you want to send to the API. And then here we're calling the annotate method, and then we'll get our analyzed text data back in that API response. So I don't like to get too far into a talk without showing a demo. So I'm going to show you a demo of our natural language API here. So what we have here is the natural language API products page. And on the product pages for all of our different APIs, you can try them directly in the browser. So there's an example sentence here. We'll analyze it. And we can see that here we get all of the different entities. So this is the entity extraction method. It tells us the sentiment of them, and it links us to the Wikipedia page for those entities if there is one. Sentiment analysis, I'm going to show you a different example of that. This one doesn't have too strong of sentiment, so I'll get back to that in a moment. Syntax, we can see that we create here a dependency parse tree that is very similar to the visualization that I had on the slide. And then this is our content classification endpoint. So it's able to categorize this, and I believe there's over 700 different categories available. So really useful if you're doing something like if you want to categorize different articles or maybe comments or reviews in your application. you can use the content classification endpoint. What?
You mind if we ask questions like on the go, or you prefer questions like in the end of the session?
Would prefer at the end, if that's cool. Yeah? Okay. Yes, I'll answer all your questions at the end. So if we try another sentence in here, I'm going to say, Tallinn is beautiful, but the weather is not great. Let's see what it says about that. So here we can see that we actually get entity level sentiment analysis. So in our sentiment data, we get this score value, which is a number. Let me make this a little bit bigger so you can all see. It's a number ranging from -1 to 1, telling us how positive or negative this specific entity is. So we can see Tallinn got a score of 0.7, almost fully positive. Weather got a score of -0.7. Weather's not great today. I heard I missed some really good weather, but I'm here for a couple days, so hopefully it'll improve. And magnitude just tells us how strong the sentiment is, regardless of being positive or negative. So this is a value ranging from 0 to infinity. So you can see here how this would be useful if you're doing any sort of review or comment analysis, where the aggregate sentiment score, which we get here for the entire document, isn't going to be so useful to us because it tells us 0 here, but actually it had quite a lot of sentiment in it. So that's where you would want to use the entity level sentiment. The content categorization feature is right now only supported in English, but what you can do is use the translation API, another machine learning API we had, translate your text to English and then run content classification on it. So that is the natural language API. So when I present on any of our APIs, I often get the question, what if you need something more custom? So the API provides a lot of useful types of data, but there's a lot of situations where you might need a custom model that's trained on your own data. So the next part, I want to talk about custom text classification with TensorFlow. To start, what is TensorFlow? Has anyone here used TensorFlow? Cool, looks like about 5 or 10 folks. So TensorFlow is an open source project, and from the beginning, the Google Brain team wanted everyone in the industry to be able to benefit from all of the machine learning projects that they were working on. So they made TensorFlow an open source project on GitHub. It's the same code base that we use internally at Google. And because TensorFlow is open source, you can train and serve your TensorFlow models anywhere. So you can run your training jobs on your own servers and your own data centers. You can run them on VMs and cloud providers. You can even compile your TensorFlow models down to ARM code and serve them directly on mobile devices. The uptake of TensorFlow since it launched, I believe at the end of 2015, has been really phenomenal. It's the most popular machine learning project on GitHub. I believe it has, I think it just crossed over 100,000 GitHub stars. So what does TensorFlow look like? I'm going to show you a diagram of what the API looks like starting from the lowest level. So at the lowest layer here we have the op kernels, the CPU, GPU, TPU's mobile device. And to execute these kernels, we have the TensorFlow distributed execution engine. What most developers are going to interact with is the API front ends. And I'm going to focus on the Python front end today. So when you're using TensorFlow, you can choose whether you want to use a lower level or a higher level API. With the lower level API, you have more control over writing the algorithms that are going to be used behind your model, defining the different operations in your TensorFlow graph. The higher level APIs abstract a lot of that for you, so you just need to know what type of model you want to choose, and TensorFlow handles the internals of that for you. So one of the higher level APIs is called Keras. So Keras is an open source project created by someone named Francois Chalet, who now works at Google. And TensorFlow contains an entire implementation of the Keras API as part of TensorFlow Core. And both of the demos that I'm going to show today use the Keras API. It's really easy to use syntax for defining the different layers of your model. So it lets you build models with high-level primitives. Has anyone here used Keras? Curious. Looks like just a couple. So you can use Keras on its own, or you can use tf.keras to get access to some of the utilities that TensorFlow provides, like the TensorFlow estimator. So TensorFlow estimators let you give you access to distributed training. So you can run your TensorFlow training job across clusters of machines without having to change any of the code in your model. You also get access to a tool called TensorBoard, which is a visualization tool for evaluating your model as it's training. And then you can easily export your model for serving. So with estimators, you instantiate your estimator, you define the machine learning algorithms and the type of model you'll be using, and you're ready to go. TensorFlow the estimator API takes care of distributed training and exporting your model for serving for you. And then finally, we have what are called pre-made estimators. These are models in a box. So basically, you just instantiate one and you're ready to go. You need to choose what type of model you want to use, whether you're solving a classification problem or a regression problem. You instantiate that type of model. You're ready to go. All you need to do is format your data get it into a format that TensorFlow can read, feed that into your model, and then handle generating predictions. So that's kind of an introduction to the TensorFlow API. I'm going to be focusing on Keras. So the first demo I want to show is building a text classification model using the Keras API. So the input to our model is going to be Stack Overflow posts, just the title, and our model should output the corresponding tag. I know many Stack Overflow questions have more than one tag. To keep things simple, we'll just use one tag as the prediction for this model. So the first step is to get our training data. So when we're building a model from scratch, we need lots and lots of data to get started. So I needed a large data set for this to work. I couldn't just pass it like 10 Stack Overflow questions and expect it to be able to predict the tag. So I'm using a data set from BigQuery. For those of you that aren't familiar with BigQuery, BigQuery is our big data warehouse tool on Google Cloud Platform. It lets you do data analytics, run SQL queries against really large data sets, and does it super fast. As part of BigQuery, they have something called the Public Datasets Program, where they've made a bunch of different data sets publicly available. Anybody can go use and run queries against them using the BigQuery API. And so one of those data sets is every Stack Overflow question and answer in BigQuery. So I took a subset of those and used them as training data for the model. So this is what the input to our model looks like, and this is what the prediction looks like. Now obviously we can't feed text directly into our model. We need to get it into a format that our model can understand, which is what I'm going to talk about in a moment. But first, we needed to get the training data from BigQuery. So you write your BigQuery queries in SQL. It also you can write them directly in the browser. There's also a BigQuery REST API, so you can run queries in whichever language you'd like. So this is the query that I used to extract my training data for this. So for this, I chose to use 20 different tags. I just looked at the top tags page, grabbed the first 20, and I took 2,000 posts from each tag. So this is the query I ran to grab that, and then I split my data into training and testing data. So when you're building a custom model, you want to use most of your data to train the model, but then you want to reserve a subset of that to test your model to see how it performed on data that it has never seen before. So for this example, we're going to use what's called a bag of words representation to represent text into our model. Because remember that we can't feed that text directly into our model. We need to get it into a numerical format that our model will understand. So bag of words is a simple type of text representation that we can use to represent each question in our model. Now how this works is you can think of each input to our model as a bag of Scrabble tiles, where instead of a letter on each tile, it's going to be a word from a particular Stack Overflow question on each tile. So what this type of model takes into account is the presence or absence of different words in a question. What it doesn't take into account is the order of words. Obviously, if it's in a bag, it's all scrambled. Which words depend on other words, or the relationship between different words in your model. And what you want to do when you're building this is you don't want to include every word in your vocabulary. So I didn't take all my Stack Overflow questions and build a vocabulary of every word that exists there. You want to take just a subset of those. So for example, I could take the top 1,000 words from my vocabulary, and then each input to my model would be a 1,000 element vector indicating whether the particular question contained one of the words from my vocabulary. So I'm going to show you what that looks like on slides. using a very simple example. So I'm going to say that I have a vocabulary of just 10 words, the 10 words listed here, and I've only got 3 possible labels that it could be. I'm just going to use this to keep things simple so that you can understand how bag of words works under the hood. So I've got 10 possible words in my vocabulary and 3 labels. And so let's take this Stack Overflow question as an example, how to redirect to another web page. Now looking at our vocabulary, oops, not going to skip ahead quite yet. Looking at our vocabulary, we can see that 2 of these words are present in our vocabulary, so redirect and web page. The input to this model for this particular question would be a 10-element vector. So every input to our model is going to be the same length. That's going to be the length of our vocabulary. So we have a 10-element vector that should have 2 ones indicating the presence of the words redirect and web page and corresponding with their particular indices in our vocabulary index. So that's how we'd represent this question to input to our model. And then this is how we will represent the prediction. So the prediction will be a one-hot vector indicating, so since in this example we only have 3 possible labels, it'll just be a 3-element one-hot vector indicating the correct label. So this is a question about JavaScript. So we can see here what the input and what the prediction looks like. The prediction is what's called a softmax vector. When our model outputs a prediction on data it hasn't seen before, it'll output this softmax vector, which just means that each of all the elements in the vector will add up to 1, and they'll indicate the probability that this corresponds with that particular tag. Obviously, with our labeled training data, we already know what tag it is, so it's going to be a one-hot vector. But if we look at an actual prediction, it might look something more like this. So it's 95% sure that this is about JavaScript, 3% sure it's Java, 2% SQL. So they all add up to 100. Here's an example for a question about SQL. So if the title of the question is join 2 tables, the only word here from our vocabulary is join. And here our model is 92% sure that it's about SQL. So now let's look at the code for building our model using Keras. Keras has 2 different APIs that you can use to build the model. In this example, I'm going to show you the sequential API. So the sequential model API is the simplest to get started with, and it lets you build your model as a stack of layers. So here I define my model as a sequential model. In my first layer, this is a dense layer, which basically just means it's fully connected. Each neuron in one layer is connected to every neuron in the next layer. And there's 512 neurons in this layer. This number is a hyperparameter that you can tune. So there's no magic answer for what's the best number of neurons in a layer. You kind of just have to experiment with different values and see what works best for your data set. So when we define our layer, we tell it the input shape. So this is going to be the size of our vocabulary. In this simple example, it's just 10, so we have that 10-element vector. This model just has 2 layers. So the activation function just tells Keras what the output of our model will look like. What type of calculation is it going to use to perform the output? So the output of this model is going to be the number of classes. In this case, we just have 3 tags in this example. And as I explained before, it's what's called a softmax vector, which just means that it's going to give us the probability that this prediction corresponds with each of our different tags. So to build our model is just these 3 lines of code, and the 4th to compile it. So which is pretty amazing. So we don't have to really know much about how these algorithms work under the hood, what these activation functions are actually doing. We can just define our code simply with these 3 lines. And then in this compile step, we have here what's called our loss function or error function. And this is how our model is going to evaluate how it performed at the specific task. The goal of our model is, as it's training, we want to minimize this loss. We want to minimize that error. We don't need to worry too much about the loss. The optimizer is going to tell our model how it's going to minimize the loss. Keras and TensorFlow come with a whole different bag of different loss functions and optimizers. But the great thing about using these higher level APIs is that we don't really need to focus on how those work under the hood, we can focus on getting high quality training data for our model, figuring out what type of model we want to use, in this case bag of words, and then using our model's loss function to evaluate how it performed. So this is how we train our model. We just call model.fit. We pass it our training data. So this would be our bag of, X train would be our bag of words, and then the Y train would be the corresponding labels. Batch size tells our model how many elements it's going to evaluate at one time. Again, this is another hyperparameter that you can experiment with. And then epochs is how many times our model is going to go through our entire training set. So every time it goes through the data once, it'll then look at the loss function, update the weights of the model, and then iterate through that training data again. This is another thing that you can tune. So obviously, you don't want to train it forever. At a certain point, it's going to stop improving accuracy. So you kind of want to see how it's doing. This is going to be very specific to your data set again. And then to evaluate how our model performed, we call model.evaluate. And that's going to give us our accuracy score back. So let's see this in action. I'm going to jump back to the browser. And I'm going to use a tool here called Collab. So Collab is, I'm going to connect to the runtime. Collab is a tool that lets us run Python notebooks in the browser. It's hosted on Google Cloud. So I can write interactive Python code, run it in the browser. I'll have a link to Collab at the end. It's just collab.research.google.com. You can go to it and spin up your own notebook right now if you'd like. And it gives you access to a free GPU. Let me make the font size a little bit bigger. Okay. So this model trains pretty quickly. So I'm going to run through the code that actually trains the model, and then we'll evaluate its accuracy on some sample input. So this is not authored by Google. It was authored by me. I'm going to run it anyway and take a risk. Okay, so in the first two cells, we're just importing all of the libraries that we're going to use in this. We're using the TensorFlow implementation of Keras, and it was tested with TensorFlow 1.8. So the next thing we want to do is we want to download our training data to this Collab instance. So I have run this query, which I have a link to, and I'll share a link to this Collab at the end. So I have a link to the query in here, and I have saved all of the results of that query to a CSV file that's hosted on Google Cloud Storage. So I'm going to download that file to this Collab instance. There it goes. It's downloaded. And I'm using pandas here, which is a Python library for doing data analytics, data science. So I want to convert this to a pandas data frame, which I've done here. So I've done pd.readcsv. That converts this to a pandas object, which I can use to run some handy methods like just show me what the first 5 rows of my data look like. So this is what our CSV file looks like. We've got our posts and our tags, just like we saw on the slide. And let's take a look at how many of each tag we have, just to confirm that this is the data that we're expecting. So again, these are the 20 different tags we're using, and we do have 2,000 of each tag. The next step, as I mentioned, is really important to split our data. A common training test split is 80% of your data used for training, 20% reserved for testing. So that's the split we're going to use here. So we're just going to define these variables, train and test size, train size to see, to extract our data. And then we're going to split our data frame into training and test data for our features and our labels. So now we're getting into the bag of words implementation. So as I mentioned before, we don't want to use our entire vocabulary when we define our bag of words. That's going to take a long time to train. There's probably maybe, I don't know, 50 to 100,000 different words in our entire vocabulary because we've got 40,000 different Stack Overflow questions. So what we want to do here is I chose 1,000. So I'm going to take the top 1,000 words from my vocabulary. This is a number you can experiment with. I tried a few, and this ended up having the best accuracy. And luckily, I don't have to extract those words on my own. Keras has some utilities for pre-processing text. So it has this tokenizer object. Is that noise coming from the building? Or okay, I didn't know if I was making that noise. All right. we're good. So it has this tokenizer method that we can use to create a tokenizer, and what that's going to do is it's going to give us access to some utility methods. So first, when we create this tokenizer, it is we're passing it the number of words in our vocabulary. So it's going to create this index for us, basically of the top 1,000 words. Each word is going to be associated with a specific index or number. So we're going to create our tokenizer, and then we are going to fit the tokenizer only on our training data. And then we can use this method text to matrix to then convert our text input into that bag of words representation. And then we're using a utility from the scikit-learn library to encode our label data. So here we're just converting all of our labels into a 20-element one-hot vector since we have 20 different tags. So here we create the encoder. And then we convert our labels in that step. So then in this cell, we're just going to take a look at the different shapes of our training and test data. So here, remember that our training data, we have 32,000 posts in our training data, and each of those posts is represented as a 1,000-element vector, because that's the size we chose for our vocabulary. It's just a vector of ones and zeros telling us if words from our vocabulary are present in that specific question. And then our test data is all 20-element vectors, because we have 20 different Stack Overflow tags in this specific problem. In this example, I am using a batch size of 32, and I'm going to run training for 2 epochs. And this is all of the code that I'm using to build my model. And here's where I'll train it. This should train pretty fast. Otherwise, I wouldn't make you wait here while our model trains. So I'm only running this training for 2 epochs. So the emphasis here isn't on accuracy. I just wanted to show you how simple it was to build a model with the Keras API. And looks like training is almost done. So now we want to evaluate how our model performed using our test data, so data it hasn't seen before. So we can see here that the accuracy is 80%, which is decent. Again, I mentioned the emphasis here wasn't on accuracy. And the number this is the number we want to pay attention to in terms of accuracy, because this is evaluating it on our test data set, data that our model has not seen before. So the next thing we want to do is let's take a look at how our model performed on some raw data. So in this case, I'm just going to take data from our test set, and I want to log how it performed on just a couple of different questions. So to generate predictions for my model, all I'm doing here is I call model.predict. Right now I'm just looping through the first 10 questions in my test data set, and I'm printing the label that the model came up with versus the actual label. I didn't print the entire question for all of these because some of them were pretty long. We can see that overall it did pretty well. This one, .NET, confused it for ASP.NET, pretty close. .NET and C# got confused there. So accuracy probably would be slightly higher if I only picked, .NET and didn't use the C# tag in my data set. But that's something I can look at. I can look at how it performed and then go back and decide how I want to fine-tune my data set there. So the next thing that I want to show you is what's called a confusion matrix. I'm not going to focus on the code for generating it too much. We don't have a ton of time, but I do want to show you what this plot looks like. Let me make that a little bit smaller. So if it looks confusing, it's called a confusion matrix, but it's actually not super confusing. We'll take a look. So what you want to see in a confusion matrix, and it's a little hard to see here because we have 20 different labels we're dealing with, but what you want to see is a strong diagonal from the top left. So what this is telling us is for our test data set, what percentage of each specific label did our model predict correctly? So the numbers are a little hard to see here, but the most accurate ones are the darkest blue. So it looks like for Android, it predicted 90% of those correctly. AngularJS, it got 98% of them right. Some of the ones it didn't do so well as were C#. Confused some of those for whatever that tag is. Let's see, .NET, which makes sense. So the confusion matrix is a really good way to see where there may be inconsistencies in your training data, where you may want to go back and fix your examples to make sure that they cover all the potential things you might see when you're generating predictions. So that is what the confusion matrix looks like. So let me see how much time we have. Looks like we have a bit of time. 15 minutes? Okay, cool. So I do have one more demo that I was going to show. I had a little more time today than I thought, so I added this one at the end. So what about a little bit more complex text analysis model? That's weird. The headline for this slide is not showing up, but hold on. So we're going to see, given a wine's description and variety, can we predict the price of the wine? Oh, there it goes. So this is what the example input and prediction to our model look like. So we're going to take the description, the variety, in this case it's a Pinot Noir, and our model will output what it thinks the price is. Now the reason this is well suited for machine learning is that we can't create explicit rules. So we can't say, like, every time the word vanilla is in a description and it's a Pinot Noir, it's a mid-price wine, whereas every time we see the word fruity, it's going to be cheaper. We can't make any rules like that. So I wanted to see if I could build a model that would be able to extract insights from this data. First step, again, since we have a custom model, we're going to need lots and lots of data to train it. So I used a tool called Kaggle to get the data. Kaggle is a data science platform. It's part of Google, and they've got a ton of great data sets on there. I definitely recommend checking it out. If you're new to machine learning and you're looking for interesting data sets to get started with, they have tons of awesome ones on there. So I found this data set that contains 150,000 different wines. It has a bunch of data on each one. It's got the description, the region it came from, the points rating, the price, different specificity by region, lots of different data. For this model, I just took the description, the variety, and the price. So I'm also going to use Keras to build this model. For this example, I'm going to build a wide and deep model. That's basically just a fancy way of saying I'm going to represent my inputs in two different ways. So I'm going to represent my inputs in both a wide and a deep representation. The wide representation is going to be exactly what we saw in the previous example. That's going to be a bag of words vector, so a very wide vector depending on what I choose as my vocabulary size. A deep vector, I'm going to use what's called embeddings. And embeddings, there's lots of blog posts out there about embeddings, so I'm not going to get too much into the details. But embeddings are a way to represent text in vector space, so that words that are similar to each other are closer together in vector space. So we use dense, deep vectors to represent our text as embeddings. So we're going to represent them two different ways. And for this example, I used, it's a little hard to see, but I'll show you the code in Collab in a minute. So I'm going to use what's called the Keras functional API. So in our last example, we used the sequential API. This one we're using the functional API. This gives us a little bit more flexibility for combining models and building models with multiple inputs. So the first step is to build my wide model. So in this case, I am representing the text as a bag of words. And then to represent my variety in the wide model is pretty simple. It's just going to be, I've got 40 different varieties in this data set. So in this example, I used, going back to the bag of words, I used a 12,000 as my vocabulary size. So each input is going to be a 12,000 element vector with my bag of words. For the variety, it's just a 40 element one-hot vector with each index corresponding to a different variety. Then I'm going to concatenate these layers, and my output is just going to be a numerical price prediction. So that's my wide model. And then to build my deep model, as I mentioned, I'm going to use what's called embeddings. And I can't feed text directly into my model, obviously, as we talked about before. I'm going to need to convert it to numerical representation for my embeddings. And the way that I do this is I represent each word as a different index. And so all my input still needs to be the same length. Not all the descriptions are the same length. So what I do here is I specify my input length as 170 because none of my descriptions are longer than 170 words. And then if we have shorter descriptions, we just pad it with zeros at the end. And then I choose, I tell Keras what the dimensionality of my embedding space is going to be. Here I'm using an 8-dimensional embedding space. Obviously, you can experiment with different numbers here and see what works best for the particular type of data you're dealing with. So this is what the input will look like. So we have a 170 element encoded vector with each integer corresponding with a different word in that particular wine description. I don't have my varieties here. I'm just representing the text in my deep model. So then using the Keras functional API, it's pretty straightforward to combine the outputs for these two models. So I get the output for my wide model, the output for my deep model. I combine that into one, and then I compile my model so that it's ready to use. I didn't include the code here for training, but it's the same as what you saw before, so I would just run fit and evaluate. So I'm going to jump to one more demo. Should be pretty fast. I think I have time for it. I've got another demo with Collab here. I'm going to make this a little bit bigger. So what I'm going to do here, this model took a little bit longer to train, so I'm not going to show you the training. What I'm going to show you is generating predictions on some raw wine description data. So I'm going to reconnect to the runtime, and the import cells look pretty similar to before. And what I've done here is I saved my model, which is a binary file, to a file in Google Cloud Storage. And Keras has this method load model, which lets me load a model that's already been trained so that I can run predictions on it. The tokenizer, which we saw when I trained my model, so that is not saved to the model binary. So I've saved it to a different file. Same with the variety encoder for the different wine varieties. I've saved that to a different file, and I'm also going to load that for when I generate predictions on my model. So like any good developer, we will ignore this warning and go on to the next step. All right, so then we're going to make some predictions on raw data. So what we have here is we have 5 different wine descriptions. So the description here corresponds with this variety Pinot Noir, which corresponds with this actual price. So we're going to see, I'll make that even bigger. We're going to see how our model performs on these 5 wines. First step is I wanted to just show you a visualization of what that tokenizer word index actually looks like. So this is a sample of it. So each word here corresponds with a different index. And then our variety encoder is just this 40 element vector with each variety corresponding with a different index. So first we're going to build the features for our wide model. Oops. Did I not run this? Let's see. Maybe I missed a cell somewhere in here. Alright, live demos. You never know how they're going to go. I'm going to reload this file. So it's pulling from another cool thing you can do with Collab is you can pull from GitHub. Oh, this already includes the output. Okay. Let me make this a little bit smaller. And I'm going to clear the outputs, and let's try this one more time. Alright, we're going to run it anyway. It may have been in a weird state. So yeah, it pulled from this file on GitHub, which you can do. You can just create a URL that pulls from any notebook file on GitHub and create a Collab notebook for it. There we go. I must have just forgot to run that cell before. I think that was the problem. All right, so we're back to where we were. This is a visualization of what the wide input to our model looks like. So we have our bag of words matrix. It's a 12,000 element matrix. I'm obviously not going to print it all here. And then this is for our first wine. So then the variety matrix is a 40 element vector, one hot vector with a 1 here, which corresponds with Pinot Noir, which is right here, which looks about right. And then we're going to create our deep representation, which is this vector that we're going to feed into our embedding layers. And here we have a pretty short description, so we've padded a lot of zeros onto it. That's just for our first description. Now that our input data is formatted correctly, all we need to do is call model.predict to generate our predictions. And in this step, I am just looping through those predictions and displaying what our model predicted with the actual price of the wine. So we can see that it did a pretty good job. This one predicted $46.4. It was actually $48. This one, it was about $30 off, but it was still able to extract that this was a more expensive wine. And we can see that it was pretty close for the rest of these sample wines as well. If you've got any you want to try it on later, we can take a picture of the description or just copy it into this notebook and try it out, see how it performs. So that is that demo. And that's all I've got. Here's some links to all the things that I discussed. If you want to take a picture of that, I'll leave it up for a moment. I've got blog posts corresponding with both of the demos, and the code for both of them is on GitHub if you want to run similar models on your own data. I don't know how much time we have for questions, but if we don't have enough time now, I can definitely take them after.
We have some, so let's start with a quick question and answer session. Any questions?
Yeah, any questions?
Yes. Good luck. Sorry.
Thank you for a good talk. You actually showed how to build a model, right? But business wants two things. Not only to build a model, but to show that it's the most optimal model, and to show that it's very easy to interpret this model. How can I use this functionality to move in these two directions, actually? What can you propose?
So are you asking about like serving the model in production and then building something that generates predictions on it?
Actually, how to prove that this model which I can build here is the most optimal, the best ones among all the others which I can build.
With other technologies, right? And why it is easy to interpret? Because TensorFlow still generates black box models.
Okay, so the question was how can we evaluate that the model that we built was the most accurate one? And we have a lot of resources on the TensorFlow blog, on the Google Cloud blog about different models that you can choose from and how you can evaluate them. One great way to do that is with TensorBoard, which I didn't show. But TensorBoard lets you, is a tool for visualizing how your model is performing, and you can look at each of the different nodes of how your model graph is actually defined. So if you want to get a little bit more detail on what each layer in your model looks like and how your model is computing the inputs and how it's flowing throughout the layers, TensorBoard is a great way to do that. There's a bunch of resources on TensorBoard out there. So yeah, I'm happy to follow up with you after and share some resources on doing that.
Any more questions?
Yes.
What about, false prevention, or like people now with machine learning, they can understand how to sell stuff, like example of wine, what to put in wine description. So people think it's like more expensive, fat benefits, or the cheating, maybe like some ethical aspects of that. So what do you think in Google? So like we provide the tool and that's it. We also think somehow on ethical aspects of using machine learning because it can be quite, dangerous in some cases. I don't know how to behave as a human, like, haircut with reservation, you show like, and then using machine learning, you can do false transactions, and behave as a human, in internet banking and that kind of things. So what to do with that?
Okay, so the question is about how to make sure you're using machine learning for good.
Yeah, in short, yes.
Okay, so that's definitely a big topic. My goal, obviously, is to show how you can build machine learning models, inspire all of you to build your own tools with machine learning. Obviously, people can build models that aren't for the best purpose. We don't have so much control over that. But yeah, that's a tough question. Don't know the best way to answer it, but one thing that's important is making sure that your training data isn't biased. So you want to make sure that the way that you went about collecting your data represents the entire population that's going to be generating predictions from your model. That's one thing we see a lot. when people are evaluating, why their model didn't perform as well as they had hoped in production, maybe the demographics of people that collected the data wasn't representative of the people that were the end users who were using it. So one thing to be aware of is like bias in machine learning data. So there are a bunch of resources online about that. But yeah, I'm happy to chat with you after more about making sure we're using machine learning for good. Good question. Yes.
General question about machine learning.
Mm-hmm.
How much, in your opinion, machine learning is about like sorcery and trial and error, and how much it's like learned systematically and science?
The question was, how much is machine learning trial and error versus more of a systematic science? I would say it definitely more skews towards trial and error. The hardest thing that I always find when I'm starting a machine learning problem is getting the training data and pre-processing it. Surprisingly, like I wouldn't have expected that when I was first getting into machine learning, but from what I found, getting the data is the hardest problem. And once you have the data, sometimes it's tricky to pre-process it and get it into the exact format you're using. But another thing with trial and error is a lot of the numbers we saw in my model were what's called hyperparameters, things like the size of the vocabulary, the number of epochs you want to run training for. Things like that do involve a lot of trial and error.
So that's one problem in machine learning. For example, in medicine,
Mm-hmm.
how to prove that answer is correct one? You get some kind of number vector probabilities that you have answer is this, but can you really decide if it's true and you base your medical decisions on it?
Right. Yeah. Hyperparameter tuning is a tricky part of machine learning. We offer, I didn't talk about today, we have a tool called Cloud Machine Learning Engine, which lets you train and serve your TensorFlow models on Google Cloud Platform. So it's essentially a managed service for TensorFlow. And there are some tools there to help you tune your hyperparameters in your model. Didn't have time to get into that today though. Yes.
So what about machine learning for machine learning? So just say, that's my data, I don't know what is all about, like just give me.
That's a good question. What about machine learning for machine learning is the question. We introduced a product in January called AutoML Vision. Let me know if this answers your question. So AutoML Vision lets you provide labeled training images to this tool called AutoML Vision. It's essentially a UI. And then what it does is you just click train. It trains a model for you and gives you access to an API for generating predictions. So you don't have to write any of the model code. All you need to do is get your data pre-processed and uploaded to the cloud. So Vision was the first AutoML product that we announced. We're working on more, but Vision is what we got right now. It's currently in alpha. If you're interested in it, you need to be whitelisted to use it, but come chat with me after. If you've got a use case, I can help get you access. That kind of fills the gap of the APIs on one side, which are targeted towards application developers, but they don't let you do anything super custom. So if you want to build any specific models that are trained on your own data, you can't do that with the APIs. On the other side, TensorFlow lets you build custom models using your own data, but does require a bit of a learning curve and a lot of data to get started. With AutoML, you need only a minimum of 10 images per label to start training a model.
Last couple of questions.
Yes.
More of a business question. When you have trained the model and you're satisfied with it, how can you use it in a business scenario?
The question was, after you've trained a model and you're happy with it, how can you use it in a business scenario? That's a great question. So once you've trained your model, what you want to do is you need to find a way to generate predictions at scale, which is also known as serving. So there's many different ways to do that. As I mentioned before, we have a tool called Cloud Machine Learning Engine, which you can take your trained model, you can deploy it on Google Cloud, and then you get access to an API for generating predictions against it. So the great thing about that is you can have the application developers on one side that are just calling this machine learning engine API. If you are building that machine learning model, you can iterate on it, deploy new versions. All the application developer needs to change is the version number in the API request. So that's one way you can serve a model. There's other tools. TensorFlow has TensorFlow Serving, which is a way to export your models for serving. So there's many different ways to serve it once you've got it trained. That's a great question, because the most important part once you train a model is generating predictions on it. Yes?
So you have shown this example of supervised learning, but is it possible to use TensorFlow for unsupervised learning?
Yes, the question was, is it possible to use TensorFlow for unsupervised learning? I haven't done that too much myself. One of my colleagues has a great talk on it from Google I/O. It's called Reinforcement Learning with TensorFlow. If you search that on YouTube, you should find it. His name is Martin. It's an awesome talk. Definitely check it out.
That's all for the questions. I believe you can catch up with Sara in private session after the talk. During this coffee break or snack break that we're having. Thank you so much, Sara.
Thanks for having me.
And also very beginner friendly, and a little present from the DEVCLUB side.
Will never trust. Don't you say a word, cause I've heard it all. You were just pain when you felt it all. Oh. Something tells me that I won't miss it. It's the first time that we can't fix it. It's irreversible damage done. The thrill is gone. Ooh, baby, there ain't no one like you. You chose to keep the truth inside. Ooh, baby, keep my all to you. All you did was tell me lies. Something tells me that I won't miss it. It's the first time that we can't fix it. It's irreversible damage done. The thrill is gone. Once you leave me, it's over. No turning back, not today. Don't you come running back now. I'm not a home for the shade. Something tells me that I won't miss it. It's the first time that we can't fix it. It's irreversible damage done. The thrill is gone. Ooh, baby, there ain't no one like you. You chose to keep the truth inside. Ooh, baby, keep my all to you. All you did was tell me lies. Something tells me that I won't miss it. It's the first time that we can't fix it. It's irreversible damage done. The thrill is gone. I won't miss this love, no. It's irreversible damage done. The thrill is gone. Thrill is gone.
Where do you go when you're young, when you're restless, when you're fun, cause you're desperate? Oh, here they come for a chance, for adventure. What's your poison? What's your pleasure? Oh, my city, she never sleeps, my city. She never weeps, my city. She keeps me alive. Give it up for my city, oh, oh. Give it up for my city, oh, oh. Give it up for my city, oh, my head up high. Now I know I can't take it anymore. 'Cause I'm feeling that I'm lost inside, trying to get over you.
Wizard, what do you see as you twist the tiles beneath our feet? What do you see?
Get ready to When you want to get off the darkest ground, but gravity pulls you straight down. Earth from a bird's eye view. You should grow feathers and see this too. When you want to get off the darkest ground, but gravity pulls you straight down.
You have to turn it on. That's the trick. Does it work now? I think so, yeah. But does it really work now? I can't know. What about now? No. I thought you had people for this.
Riddle me this.
There's one button over there. Now? Ha! Much better. You know, you have a lot of buttons on this one, but the right button is over there. Good. Welcome. Thanks for having me. As he said, I'm Chris. I work for Twitter, obviously. Right? I was just talking to him, and he said he saw me in a pink shirt. I said, I don't think so, because I only have this one shirt. Right? So if you're going to watch a YouTube video where I give a presentation, you will see me in the exact same outfit. So it's very easy to spot me. Okay, so usually I say the most important question is who in this room has a Twitter account? That's a pretty good outcome, but I think it was like only 50%, so a bunch of people need to create an account. But for today, I think the more important question is who does not have a beer? Who would like to have a beer of the people who don't have a beer? You should grab one. Or I'll bring you one during the talk. I'll cater you. I'll bring you one. Okay, so the reason I was asking about the Twitter account was the Twitter has a small VM team of about 4 people. We have 2 other people that are doing different things, but we have 4 core people that actually work on the JVM. Yes, I was told not everyone here is Java, right? So who does not do Java and knows a lot about JVM and 1? Okay, 1.5. Does not, yeah, right. So I'm talking a lot about the JVM because I'm a compiler engineer, and so I'll explain to you a bunch of things later, and I'll ask you if you know what it is, and then I'll explain it to you. So Twitter has a small JVM team, 4 people, roughly. So we have 3 GC engineers, and they're basically constantly busy fixing the GC issues that everyone has. We have our microservices, and some of them don't work very well, and so they're constantly working on this support-wise, kind of. And then there's me. I'm the compiler engineer, and I do the fun stuff. Okay, so and I travel around to Tallinn and talk to people. I mean, I can turn it back on, but I'm not sure how long it will last.
many engineers.
I think it's these two.
Right.
Okay, so it takes 3 engineers.
Great. The answer is
No.
okay. It's okay.
Still working. See? Didn't break it. All right, we were back. Where was I? I can't remember. So everyone got a Twitter account now? Okay. So I do the fun stuff, and I travel around and talk to people about the stuff we do at Twitter. And so if you're going to tweet about this talk, and I encourage you to do that, I hope you tweeted about the previous talk as well. Doesn't seem like it. If you're going to do, please add this hashtag TwitterVMTeam, and then my colleagues back home, they will know that I was actually here. Good. So what's the goal of this talk? You know, the talk name, I saw it was kind of cut off. It's actually a talk name is Twitter's Quest for Holy Grail Runtime, right? And so what's the goal of this talk? And the goal is to save money, okay? It's definitely a goal for Twitter to save money, but it would also be good if you could then take away what I'm telling you today and save money yourself. You know, not personally at home, well, maybe, I don't know, but at your company, right? And then, you know, maybe the company gives you a bonus or something like this, I don't know. Well, so let me quickly talk a little bit about myself. My name is Chris Thallinger. I live in Hawaii. I don't know if you've been there. I'm running a small conference called Lava 1, which is not so funny anymore now that it's called Oracle Code 1. It was really funny when it was called Java 1 and Lava 1 in Hawaii, right? So it's in January. I don't know. How's the weather in January here?
Like in Hawaii? Snowing here.
So we were running around in orchards and surfing at that time, I'm just saying. So if you're busy or not busy, if you're free in January, maybe you should stop by. So I'm working on JVMs for a long time, over 13 years now, and almost all 13 years I was working on compilers, JIT compilers. Number one question, who knows what a JIT compiler is? Oh, that's pretty good. I almost don't have to explain it, but a JIT compiler basically in the JVM takes Java bytecode and translates it into native code so that your application runs faster during runtime. So that's kind of the gist of it. So I'm working on this stuff. Back in the day, oh yeah, at this point, I would like to call out people, like old people, right? Who remembers what GNU GlassPath is? Ha, 1, 2, 3. Old people. GNU GlassPath was a clean room implementation of the Java core library before Sun open source Java, right? And so it was a GNU effort to do that. There was also Apache Harmony. They were really the bad guys. Even the Sun guys were better than Apache Harmony. That's not true, but you know, there was always this license war, and it's still going on. So we always met in at FOSDEM in Brussels. I don't know if you've ever been to FOSDEM. You should definitely go. So there's a lot of beer drinking going on, even more than here, I have to say. And so we were kind of the Wild West, and we were doing all this free Java stuff, right? And then Sun, they were the bad guys. And in 2007, 2008, Sun then open source Java, right? And then suddenly they showed up at FOSDEM, and then they also gave presentations and wanted to, you know, become cool guys as well, I guess. And they were buying us beer, and so we said, okay, yeah, you're cool too. And so they're still coming and buying us beer, and so we let them. Really, that's how it works. And then in about 2009, I thought, okay, yeah, the Sun people, they are actually pretty cool, so I started working for Sun Microsystems. And at that time, I joined the Hotspot compiler team, and I worked mostly on C2. Who knows what C1 and C2 are? Okay, a few people. So Hotspot, you know what Hotspot is, yes. The JVM in OpenJDK. Hotspot has two JIT compilers. One is called C1 or client compiler, and the other one is called C2 or server compiler. You might remember the dash client, dash server thingy. So there are two JIT compilers. There are two different compilers. One, C1 is a high throughput compiler. So the purpose of the compiler is to produce native code quickly. So you get away from interpreting code and run on native code, but it's not optimizing as much. And then C2 is a highly optimizing compiler, and it produces peak performance code so that your application runs really fast. That's how it works. So I was working on C2 most of the time. And then these are kind of the three biggest things I've worked on besides on fixing $1 million bugs, I think. I was working on JSR 292, which is invoke dynamic, right, for dynamic languages, so the support for that. John Rose and I, we were working this for, I don't even know, a long time, 2-3 years or something like this. I wrote all of the compiler support, I did a little bit of interpreter support, and then there was a first implementation that didn't work so well. It had like a performance cliff at some point when you did too much. So we had to rewrite that whole thing, and we moved a lot of the logic from the VM, from the C++ code into Java, into the core library. And I wrote a bunch of that core library code as well. So if it doesn't work, you technically could blame me. But a lot of people touched the code after me, so I think my code was perfectly fine. Exactly. So then we were doing JEP 243, the Java level JVM compiler interface. We're going to talk about this a little later. JVM CI in JDK 9, which is basically we took, who knows what Graal is? Okay. So that's kind of good that no one, not really, but you might have heard, the people who put their hand up, you might have heard of the Graal VM announcement, right? I'm not talking about Graal VM. So that's a very confusing marketing term that Oracle Labs came up with. So Graal VM includes a bunch of more things. It includes, Graal the compiler, it includes Truffle, it includes Substrate VM. I'm not talking about these things. The only thing I'm talking about is Graal the JIT compiler, nothing else. And Graal the JIT compiler, I think I'll bring that up later on the slide, I think, is part of OpenJDK now. So that's the only thing I'm talking about. So we took the interface. Graal is written in Java, by the way, if you don't know that. And so we took the interface that Graal had and extracted it out of Graal and put it in the JDK. So that the idea behind it was, if we have the interface in the official JDK, in Oracle JDK or OpenJDK, you could just download a build from the Oracle website, and you can plug in an external compiler. So that was the whole idea. So we put that into JDK 9. And then we did JEP 295 ahead of time compilation, which is basically using Graal to AOT compile Java code. It's kind of a command line Java tool, really. It's nothing more. It reads in Java bytecode class files, jar files, throws it at the compiler compiles it and spits out a shared library. That's all it does. So since JDK 9, there's also Graal in the JDK, basically. And it was funny, at FOSDEM this year, I gave this presentation, and then I said, well, you can use it in JDK 9 as well. And then later Mark Reinhold came to me and said, well, I didn't know that worked. And I said, well, yeah, So I made it like that. I made it so it works. And now I'm working at the Twitter VM team. Best company on the planet, by the way. I mean, I'm sure this company is good here too, but, So everyone, or maybe not, because like 50% didn't have a Twitter account. You kind of know what Twitter is, though, right? Yes. So it's a hugely distributed system. We have many, many, many microservices. The most important ones are obviously the tweet service, reading and writing tweets, user service, everything that has to do with your account, your user, timeline service, building up your timeline, social graph service, the interactions, the who you follow and who is following you. So these are kind of the biggest services we have, biggest in terms of the instance size, like how many instances are we running of that service. And so we have many JVMs running the service, depending on, is it one of the bigger ones, and it's thousands of machines running thousands of JVMs. So, and we do that in multiple data centers. So it's kind of a big operation, right? We use a lot of open source, but we also do a lot of open source. So we have this GitHub jokes? Anyone? You know, I've seen a couple good ones today, I have to say, on Twitter, good ones. It was mostly Clippy, but, you know. So we have this organization on GitHub where we open source all the stuff that we can open source, let's put it this way, right? We are not open sourcing our IP, but we open source all the frameworks that we use to build stuff on top. Like we have something called Finatra, that's the framework where we build most of our microservices on top. You can download that. So in general, Graal is also open source, and so it's a good fit for us, right? We can pick it up from GitHub, and we can integrate it into our JDK, and then use it. And we're also contributing back to Graal as well. I'm talking a little bit about that later. So we have our own JDK, or VM team, as we call it, and we have our own JDK. So it's pretty much a clone of JDK 8U. We're still running on 8, yes. And the main difference is between like the upstream 8U version and our version is we have JEP 243, right? We need it if we want to run Graal on 8. We have to have it. So we backported it. We have a copy of Graal in there. We have something called Contrail, which is not that important anymore because, or will not be that important anymore because Oracle open source JFR, Java Flight Recorder, and I think it will be part of 11. I hope so. And then at some point we had a bunch of CMS improvements, but we upstreamed all this stuff. So I should probably take out that line off my slides, but you know. So why Graal? That's a very important question, right? So C2, and I've worked with C2 for a very long time, is very, very complex. It's unbelievable. The problem with C2 is it takes you multiple years to understand how it really works and how it interacts with the VM. So we had this issue when I was still working at Oracle that you know, some people weren't so happy about this is live streamed. I have to you know, be a little bit careful what I'm saying here, but some people weren't too happy with how Oracle does business, like engineers. So we were hiring, some people left, and then we hired new people who have not worked on Hotspot or C2 before. And so they started, you know, working on it and they started learning it, and then at some point they didn't say it, but they quit. And the problem is, you know, these days you're looking at frameworks and all this stuff that's on GitHub and blah, 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 and you look at it for a week or two or a month or two, and you think you'll understand, right? At that point, you will understand how it works, and you can work with it or even contribute to it or something. With C2, it's completely different. It's like me personally, it took me at least 3 to 4 years to fully understand how it works. And it's for today's society, like instant gratification, right? Like on Instagram, it's impossible. So people left. We hired them and then they left because they probably thought, oh, I'm stupid, or you know, I don't have the time for this. I don't know what they were thinking, but that's a problem going forward because we need younger compiler engineers to keep, you know, the thing running. So the learning curve of C2 is way too steep. There were no major optimizations in the last couple of years. So there were a bunch of optimizations in more the lower level situation, like intrinsics, compiler intrinsics. Intel was doing a lot of work there, right? Intel was bringing out AVX instructions wider and wider and wider. And so, and its intrinsics are basically handwritten assembly code that then gets compiled into your code. That's kind of what intrinsics are. And so this was more or less the only optimizations we did. There was no improvement of the whole inlining or escape analysis or anything. So, and for a couple of years now. So we need something where we can do these things again. And one of the main reasons why we didn't do new major optimizations was because it's too complicated. No one really wants to touch it and change too much in the compiler because it's been working so well for everyone in the last 5, 6, 7, 8 years, right? And to be honest, almost the whole world runs on Java. Like maybe it's changing now a little bit, but let's say almost the whole world runs on the JVM. It's crazy. So, and in my personal opinion, C2 reached its end of life a long time ago. So, either way. Graal, on the other hand, is much, much easier to understand. For 2 reasons, I think. Number one, it's written in Java. So C2 and Yeah, especially C2, and hotspot is written in C++. I mean, maybe some people in here are doing C++ or still can do C++, but younger people, they have no fucking clue what it is, right? So I think that's a big point. And then Graal was from ground up modular designed. So C2 was never that way. C2 is like the thing you don't want to touch because everything tangles into everything else. We've had this many times. And it's all in the bug database. It's open source. You can look at it. You touch something here and you break something over there, and you have no idea why. That's where the 4 years are coming from. That's what I was talking about earlier. So Graal is very different. It has this modular design, and it makes sure that you don't have circular dependencies between your. They call it modules. It's not really a JDK9 module in that sense, but something similar. So they make sure you don't have circular dependencies or dependencies in directions you shouldn't have, and things like this. And then, very, very important, and we'll be talking about this later a lot, Graal has just a better inlining implementation and as well a better escape analysis implementation. So it's not important that you fully understand what that is, but it's good that you heard it at least once. So I was starting at Twitter about 2 years ago now, roughly, and it was an interesting ride. And one of the reasons why I left Oracle and joined Twitter was Graal, the compiler. That's also one of the main reasons why I'm here and talking to you and talking to all the other people at the conferences I'm going to, is we need people to try Graal. We need to throw, you can only run so many times spec GBB with your new compiler until you found all the bugs, right? And it's not getting any better if you do that 1,000,000 times. So what we really need is to run your shitty production code with Graal. That's what we really want, because then we find the problems, right? So that was also the reason why I joined Twitter, because I wanted to go to a company and actually use the compiler in production, like in the real world, not in an isolated lab where nothing can go wrong. So when I joined Twitter, we found a few bugs. So I'm walking you through them. If you don't understand everything, that's fine. I just wanted to show you kind of what they were and how many we found. So the first bug we found was Graal should support the same OSR compilations as C1 and C2. If you don't know what on-stack replacement is, it doesn't really matter. Just follow along a little bit. So if you do a print compilation while you run stuff, you see all the compilations coming out, and then sometimes it says compile skipped. And in this case, it was OSR with locks not supported. And the exception that is thrown looks something like this, which is very nice because Graal is written in Java. So if something goes wrong, you get a really nice Java exception. And then it says, okay, it happens in the on-stack replacement phase, blah, blah, blah. So something went wrong there. And you could technically debug it if you really wanted to. So I discussed this with an engineer at Oracle Labs, Tom. And so after a little bit back and forth, we decided it's not a big issue because who knows what tiered compilation is? Tiered compilation? No hands? Okay. One. Okay, explain it. No, I'm kidding. So when I talked earlier about C1 and C2, the way the JVM or the way Hotspot works today, and many other JVMs do that as well, or VMs even, you start out interpreting your code, right? That's really slow. And then you jump up one tier, you compile it with C1, and you compile it in a way that you collect profiling information, and then you run a little bit, and then until you have enough profiling data, and then you recompile with C2 to actually get peak performance code. And so you're going through the tiers, and that's what tier compilation is, right? So in that case, if we can't compile in the highest tier with Graal in that case, right? If we can't compile it, the compiler says, I can't do it, sorry. We still have C1 code. So we still have natively compiled code. We're not interpreting it. So we said, okay, whatever. We try to compile it a bunch of times, and then the VM will say, sorry, and then we run on C1 code. Perfectly fine, because in this particular case, it was, I think it was a core library method, but it was not a really hot one. So it was not important for the service to run on perfectly, basically. So it was fine. But it would still be nice to get it fixed. And then at some point, I didn't even realize, I forgot his real name. I think his name is Leopold or something like this. He fixed it. So, and it was a fix of 1,000 lines of code. So, you know, it was kind of, you know, a medium type of fix. Good. So that one was fixed. That was nice. I tried to, you know, verify that it was really fixed with our service to see if, and then this other one showed up where it says no object replacement, no generated, right? So we were talking about this, and then Tom says, do I have a mouse here? No. So I have to do this. You want the dog? Yeah. So there's a problem with de-optimizing on static field access in the CL init method, which is the static initializer of a class. And so he says, Tom said, there's a little piece of logic in C2's parser which allows access to static fields within the CL init for classes which aren't fully initialized yet. So it's a mouthful, but it's basically an issue when you're compiling the static initializer. You're seeing final fields, but they can't be final yet because you haven't run the initializer yet. So the little piece of code here, the little bit of logic in C2's parser looks like this. That's the C++ method. It's called static field OK in CL init, which is fine because you are the compiler. You know it's fine, right? You know, okay, when I'm done running my code, this will be a final field, and it's cool. So you can optimize that. And the important comment is this one: better to check now than to de-optimize as soon as we execute, because usually you're not compiling a static initializer. You only run it once, right? How would that ever get hot? So if it's really being compiled or scheduled for compilation, it's either very long, so it takes a long time to run, or it has loops in it, which also means it will run for a long time. So you really want it to be compiled because your whole, well, maybe not the whole VM, but at least one thread or multiple threads in your system are waiting for this class to be loaded so that they can carry on. So if you would compile that in the way, people probably don't know what de-optimization is, right? Either way. So if you compile it in a way that you would de-optimize, that means you would fall back from the compile code into the interpreter and running slow again. You completely defeated all the point of compiling it, because you spend time to compile it, you run the compile code, you noticed, oh, I can't, so you fall back in the interpreter. Complete waste of time. So all we need is this method in Graal, 31 lines of code, 6 deleted, very simple fix. But we just needed to find this, right? That's the whole point. Good. Then we had this one, ignore the long, but it was a segv, like a crash, hard crash. The important thing here is long-running processes, couple days. That was very annoying, you know. We were running this service and it crashed after a bunch of days and I didn't know, okay, what am I doing now? So it turns out that we're using something called Heapster, which is an agent, and Heapster is a agent library to do heap profiling, okay? Heap profiling, very important. So what heap profiling means, you're instrumenting the code with some code that that collects the types, the classes that you're actually allocating, right? So that you know what you have on your heap. So remember, Graal is written in Java, okay? So there are things in Graal that are called snippets. It's something like an intrinsic, and snippets are handled very in a special way by Graal itself when it compiles it. So the problem was that Graal used these snippets, and wait, don't I have on this slide? Oh yeah, here we go. Right. So there was a snippet for yeah, I can't remember which it was. It doesn't matter which it is, but the snippet itself used the double dot value off. And the double dot value off does a new. And the new will get instrumented by the agent. So in this particular case, the snippet, you had it compiled basically into Graal, let's put it this way. And then later when the agent instruments the code, the bytecode looks different than the native code. So the bytecode was then suddenly longer than you actually native code, and the bytecode indexes were wrong. So that's why we crashed. So then Tom said, well, we don't have a good way around this, and then Doug said, well, maybe it's time to bite the bullet, to parse the bytecodes for snippets directly. That's what they did. Only took 2,800 lines of code to do that. But it was important, because a lot of people are using agents in the real world, right? Yeah, SpecGPB doesn't, of course not. But we do, right? We use that stuff. So it was very important to fix that bug. Then we had I was running a service, and I was looking at the log files, and sometimes there was an endless flood of connection exceptions that we were getting, and we really didn't know where they were coming from. The big problem when everyone, when people say, oh, microservice architecture is the best thing in the world, yeah, debug it. Right. You don't know where the connection error comes from, right? It could be you, it could be the other 100 services you're connecting to. So at that point, and I'm really not an expert in doing stuff like this, right? I was only compiler or engineer and not a microservice or whatever. I didn't know what to do. I didn't know how to find that issue. So I knew that I think what happened at this point was we were upgrading our Netty version internally, and I thought, okay, it might be a good idea to run the Netty tests with Graal to see if it will be fine. And so it turns out that Netty buffer test suite failed. I thought, okay, that's interesting. Let's look at this a little bit. So again, I talked to Tom about this situation, and it turned out that 2 bytes, or yeah, it was actually 2 bytes, were written in the wrong order. So if you know the number class, so integer short and all these long, they have a reverse byte method, and that method is being intrinsified by the compiler. So there's some specially, it's not a handwritten assembly code, because Intel has one instruction that does that, right? Reverse bytes. So that's what the compiler uses when you use that method, and it was used in the wrong way. It was short dot reverse bytes, and the compiler screwed up. But this is used all the time. So the question I still don't have an answer for is, why did it fail in this particular case, but not all the other cases that we were using? So anyway, so Tom looked at this issue. 5 changed files, 68 additions of code, 18 deleted, and I think the 68, it was basically a 2-line fix. It included a test case, that's why it was 68 lines of code. And that was it. These were all the bugs we found. And that's more than a year and a half ago now. And since then, nothing. We've not found a single bug since then. And we are running a lot of code in Graal. What are they doing down there?
We are finalizing construction.
Was that? Yeah. I'm wondering, was that finalizing? Was that a pun? Finalizer? Jeez. Yeah, okay. Yeah, no, I got it. That was a good one. Almost as good as the GitHub jokes. So, contribution. So far, we only contributed one thing because, as I said, no, maybe I didn't say it, but I said it earlier. I joined Twitter for a reason, right? So to run Twitter on Graal, to test Graal and make Graal a more mature compiler. Turns out the 2 years I'm at Twitter now, I wasn't doing software engineering. I was doing social engineering. And the reason for that is, you come to a company and, we could argue that Twitter is a kind of important service that should stay up and not, go down. It's not that easy to go to service owners and tell them, hey, I have this new compiler, it's experimental, no one's using it in production, would you like to try it? Yeah, that was tricky. There was a lot of social engineering hand-holding going on, so that's basically what I was doing all the time. So the only thing we were doing, or what I was doing, was implement support in Graal, or partially, it's still not fully done yet. And there's something called compact strings since JDK 9, and we knew we wanted to move to 9 before Oracle decided, okay, 9's not an LTS, and they screwed us all. But at that point, we still thought, oh, we're moving to 9. And so I knew compact strings would come, and I knew some services would use it, and there would be a big performance hit if we didn't have the supporting GRAL. And so I started porting 1 over because it's a little unfortunate, but Oracle decided, because C2 was a too stupid compiler to optimize the code if it was written with unsafe. That would have been much, much better, because then we could have reused the code for every compiler we have. But C2 couldn't handle it, and so Oracle decided to write handwritten assembler code. And that means that handwritten assembler code we have to port over to GRAL as well. And there's an optimized intrinsic for this, uses SSE, AVX, AVX 512, you name it, all the bells and whistles. And we needed that in GRAL as well. This is just a benchmark showing, if you look at the third line here, that was before and that was after, right? And so on the bottom table is basically the same as with C2. GRAL's not better here or anything, right? It's handwritten assembly code, it's the same thing. It's just, it should be the same. So we did that. I did not really finish it because I started traveling too much and going to conferences, but Dmitry Samosov, he then eventually finished it, wrote a test case for it. It was about 1,000 lines of handwritten assembly code that we had to port over. But it was more like copy-paste, not really doing work. But there's still, I think, four smaller methods left that we have to do. And I have to hurry up with that because I think the train for 11 will leave soon. So we should get that in before 11. I'm wasting a lot of time here, but I think you're all still happy. Your beers are still full. Probably not. Here's the important part, or the interesting one. So we're talking numbers. So you'll see a bunch of graphs, and then I'll tell you how much money we save. So we're talking about the tweet service, which is reading and writing tweets. That's all it does. It's a Finagle thrift service. So Finagle is one of these frameworks that we open sourced. It's an extensible RPC system for the JVM used to construct high-con services, whatever. We're doing this stuff. And the important thing on this slide is it's almost entirely written in Scala. It's like 92% it's Scala code. And so the test setup I used was, I used a dedicated machine for the benchmarks, because if I used it in our production cluster in the data center, we're running multiple services on one machine, right, to utilize our machines, and then there's a lot of cross-talking going on, and so it was not that easy to totally isolate the performance improvements we were seeing. So I'm using dedicated machines. And all instances that we have, so we have a dedicated machine per instance / configuration, and all instances receive the exact same requests. Very important, not the same number of requests, the exact same request, because it's important if a tweet is 1 character or 280, right? It's very different in terms of how much memory you have to allocate to process that tweet. Okay, so then we were using JVM CI 0.30, not important, GRAL, not important. We used it in the default tiered setup. I explained to you what tiered compilation is, now everyone should know, with C1 and GRAL, okay? And then GRAL bootstrapping is, since GRAL is written in Java, and we are still running on Java 8, where there's no AOT compilation, we have to compile GRAL itself when the VM starts up, right? When it gets hot and starts compiling stuff, it will compile itself. That's what's called bootstrapping. That can be an issue, but mostly it's not. If you watch my other talk on YouTube, I think I'll mention it later, I'll show you that it's not an issue. For most people, it's not an issue. And the reason is because C1 is such a quick compiler that it's fine. Okay, so, but if it would be an issue for you, and you run on JDK 9 or later, you could AOT compile GRAL, and then all this is a non-issue. Okay, graphs. That's good. It's good that it's cut off here, but this is 24 hours of tweets, reading, and I'm showing you C2 in blue. It's not that important because there's no y-axis anyway. So blue is C2, then we have GRAL in orange, and then I threw in JDK 9 as well, just to make sure. When I was doing the experiment, I was still thinking we're moving to 9, so I was throwing them in as well. As you can see, they all receive the exact number of requests, and as you cannot see, and I'm happy about it, is there's no y-axis, and that's because I'm not allowed to tell you. That's confidential information I'm not allowed to tell you. Okay, so let's go. The tweet service uses parallel GC, so we're looking at parallel scavenge cycles here. It's a moving average of 60 minutes, so it's a little smoothed out and it's easier to read. Kind of looks like the graph we saw before, right? The more tweets you do, the more memory you allocate. Makes sense. I said earlier that Graal has a better escape analysis implementation, so that means it should be able to get rid of object allocations, get rid of more object allocations than C2. So what we would like to see is like a lower graph here for Graal, which we do. Okay, that's great. That's really what we want to see. This is JDK9. This is JDK9, so it's about the same. And it's roughly 2.5% less of GC cycles. It's not a lot, right? But it's still nice if you don't have to do the GC. That's a lot of time. And especially, that means that you're not producing as much garbage, which also means you're not allocating the object. That's also where you save a lot, right? The object allocation takes a lot of code in compiled code. It takes a while. If you don't have to do this, your code is a little bit tighter and it runs faster, okay? So this is very good already. Then I have to talk about old gen usage a little bit, because our, and probably at your company as well, if you have SREs or something like these, people who take care of services, they monitor the services really closely, right? And so some of our SREs, they were screaming out, oh my God, memory leak. And I said, no, not really. It's just 40 megabytes more. So there's a 40 megabyte memory usage more in the old gen, and the reason for this is Graal is a Java application. It has some state, right? It needs to store some stuff, so it's using up a little bit of memory, but it's 40 megs, right? It doesn't matter how big your old gen is. If your old gen is 100 megs, it's 40. If it's 2 terabytes, it's 40. Doesn't matter. It's just the state is the same. There's also the same is true for Metaspace, because you have to load some classes as well. But for Metaspace, I don't have a pretty graph, so just believe me. And Metaspace is between 20 and 30 megabytes. So that's what you lose. This is the important one. User CPU time, because if you can reduce user CPU time, then you can save money. Because if you can process more tweets or whatever you're processing more requests with less CPU, that means you could actually do more, right? And then reduce the instance size of whatever you have. So we would like that to be lower, and that's definitely the case. This is about the same as the blue one, C2, and this is for 9. And I put this in a ratio, and now it would be good to see it over here, because then you kind of can't tell. You see that? Okay. But it's not, so it's roughly 11% less. And 11% is huge, right? I mean, I don't know how many compiler engineers are in this room, but if you worked on a compiler before and you tried to optimize something, you have a good idea for an optimization. If you get 1%, you're happy. If you get 2, that's great. I mean, but 11 is unbelievable. So 11% reduction is, when I saw it, I didn't believe it, to be honest, but it's true. It's really true. So the tweet service right now runs 100% on Graal in production for at least 10 months now. It might be 11 now. I can't remember. What month is it now? June already, right? Yeah, it could be 11 months now. And without an issue, right? I didn't lose any tweets. Did you lose any tweets? It's Twitter running fine, I think so. Are you reading all the Trump tweets and the GitHub tweets? Yeah, no, it's running fine. So, and it's not only the tweet service, where all the other ones, all the big other ones that I was mentioning, they're also running on Graal. 100% in production since 10 months, 11. No issue. So I was interested in this. If the improvement, the 11% that we're seeing, if it's coming from escape analysis, if the better escape analysis implementation is responsible for this big reduction in CPU time. And so I was running the experiment, and I turned off escape analysis for both compilers, for C2 and GRAW. And this is a slightly different graph. It's again 24 hours, but I had to rerun the experiment, and I'm only doing C2 and GRAW in this case. And I turned off escape analysis. So what we want to see here is exactly the same number of GC cycles, because that means they're allocating the same amount of memory, which they do. Perfect. So the setup is fine. And now let's look at user CPU time, but it's still better. And if we put that in a ratio again, we see it's still 5%. So just the implementation, the inlining implementation of GRAW gives you already 5%. And then the remaining 5 to 6% is getting rid of all the object allocations. So inlining is the mother of all optimizations, right? If inlining works well, you can produce tighter code, and inlining opens up the whole world for all the other optimizations to work well. So this is great. I was happy about this. So how much money? How much money do we save? I couldn't show you a y-axis. Do you think I can tell you how much money we're saving? Of course not. So I'm making up this fictitious company. I don't know. Some of you might know how many servers you have. Some of you might know how much money you are spending for running your business. So I'm just making this up so that people kind of understand how to get a feeling for it, how much that could be. So I was looking up cloud hosting providers, and they all kind of showed in different numbers, and it's a little hard to read. So I calculated it out for you. It's between $72 per year per CPU core and $210. Okay. Number one takeaway: if you pick the wrong cloud provider, doesn't matter which compiler you use because you're screwed anyway. So the average would be $127 per year per CPU, because we're making everything up, so it doesn't really matter if it's correct or not. So how many cores are we talking? Okay. So I was looking up, and I found this Bloomberg article from 2014, which is now already 4 years old. And it talks about Amazon, over 1.5 million servers, and Gartner says maybe 2 million. And then it says over here, Microsoft has 17 regions, and Steve Ballmer said the company had over 1 million servers with its data center infrastructure, and that Google had even more. Ridiculous numbers are these. I mean, Twitter's not as big as, let's say, Amazon or Microsoft and Google, but we have a good size. But this is ridiculous because we're talking servers here. A server has usually, what, 24 cores? So it's a lot. So we're picking a random number of 10,000 servers, and then it's usually 24 cores. So we say $127 per year per CPU core, multiplied by 24, multiplied by 10,000 is $3 million just to run whatever you're running, right? Let's say you're running Twitter. I don't know what you're running. If you can save 11% of that, that's over $300,000 per year. That's more than I get paid. I don't know how much you get paid, but it's more than I get paid. Can we squeeze out even more out of GRAW? Like, can we get even less CPU utilizations than we already get out of? I mean, the other experiment I did that was like out of the box. I didn't change anything. I was just turning on GRAW. That was all that I was doing. So easy job. So it turns out we can. So I was sitting down an afternoon, fiddling around with some inlining parameters that GRAW had, and like 2 hours or something. I can't remember, 2 or 3 hours maybe. And so I was running this experiment. That's actually the same as the first one we've seen today, and I've added this experimental color in purple here, and I've just adjusted some of the inlining parameters, inlining a little bit more. That means escape analysis can work better and so on. So we're looking at the same graph of scavenge cycles again, and it's slightly better. That's good. How much is it? It's like a 1.3% more, which is, a lot. It's like, what, 50% more. That's good. If we look at user CPU time, it's also less, which was expected. And this is an additional 2%, which was, how much was that? Like $30,000, $60,000. per year just by playing around a little bit with parameters on the command line. That's not what a human should do, right? But I think there's something called machine learning. I don't know exactly what that is, but I think machines could do this for us. And that's something we are actually doing right now. So we have something called AutoTune, and we're using AutoTune to tune different JVM parameters, like GC parameters, but we also do it for Graal. I'm not telling you too much about it because that will be my next talk then. Not today, but the next I'm preparing, and then I will tour around. I'll come back and tell you about that next time. It's very exciting, by the way. It's more than 2. That's all I can say. So any official support? I think that's a very important question. I'm probably going over time, but it doesn't matter, does it? Does not. Yeah. Hey, the sun's still up, man. It can only be, what, 6 p.m. or something? I don't know. So I'm pretty sure your company does not have its own VM team. Right. So official support for you is probably important. So as I said earlier, JDK 9 contains already Graal because of AOT. And you also can use it as the JIT compiler. It's not really supported. You know, as I said, I made it so that you could use it. But it's even better because in JDK 10, Oracle officially put Graal in the JDK, into OpenJDK. Under JEP 317, experimental Java-based JIT compiler. And that's, you know, the best support you can get today. It's it will not happen, but if your system goes down or your data center burns down, Oracle will not pay for that. But at least if you find a bug or something, or you have an issue, they will help you out, right? Okay, that's already good. Then how do you use Graal? And that's the thing I was talking about earlier. So there's this other talk called Graal, how to use the new JVM JIT compiler in real life. Very important because the fact that Graal is written in Java, it has very different properties than the compiler written in C++. And if you understand that, then you're using it right. So just search it on YouTube. There are a bunch of versions of this talk on YouTube already. And then there's something called Project Metropolis, which was proposed September 30th last year by John Rose. And the important thing here is blah, 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 advanced Java. John likes to call it Java on Java. I was never okay with that term, but he calls it Java on Java. Implementation techniques for hotspot. Our starting point is earlier proposals for using the Graal compiler and AOT static compilation technology to replace the hotspot server compiler. So to replace C2 with Graal, yay, that's what I want. And possibly other components of hotspot. So what we're trying to do is to write more of hotspot in Java, because it's easier sometimes to do it. Not all of it, like the GC, don't write it in Java. Worst idea ever. People have tried it. Maxine, CheckSRVM didn't work. But the compiler is the perfect example to do this. And it works perfectly fine. And you can do other things as well. I'm hoping we can do the interpreter, and I'm pretty sure it's possible. There are ideas to do this, but that would be great. Okay. So I have to say this, because this all looked great. Right, and you probably can't wait to get back home and try this all out, and I can't blame you. So I said most Twitter services, maybe I didn't say it, most Twitter services are written in Scala. So we only have a handful that's written in Java. And the fact that they're written in Scala is the main reason we are seeing such a big improvement. Scala, the way Scala is compiled down into bytecode, it's like the resulting bytecode is more complex than for Java. It's like I like to say Java bytecode is very flat and static. It's very simple. Scala is the worst, to be honest. But Graal can handle it really, really well. So if you're doing Java, it's a different story. With Java, my rule of thumb is it's a 50-50 chance if it's better for you or not. I've seen cases where it's better. I've seen cases where it was much better. I've seen benchmarks especially where Graal was worse than C2. And one of the reasons for this is, and I think it's the main reason, for the last 10 years at least, C2 was optimized for Java code. And more importantly, vice versa. The Java code people wrote was optimized for C2 because they wrote it in a way that it was running the fastest, right? And that doesn't necessarily mean that works well with Graal. So, you know, your mileage may vary here, but it might be possible that you're seeing some improvements there as well, but not 11%. I'm sorry. Good. I'm actually done almost. So the summary of this talk is very simple. That's it. These are the command line options you need to use to turn on Graal. That's all you have to do. If you watch my other talk on YouTube, you will see I'll do everything from scratch in my other talk. I'll fire up a completely empty cloud instance that doesn't even have Java installed, and I show you everything that you have to do to run with Graal. Switching to a new JIT compiler is very different. Some might think, I don't know. Some might think, oh God, if I'm switching GC, that's the worst, right? That's very different. GC implementations have very, very specific properties, and they're very different from each other. For the compiler, it's a completely different story. You compile code. That's all you do, right? So you can turn this on. I'm pretty sure it will not crash. If it does, I would be very happy. I would encourage you to file a bug on GitHub, and then we'll fix it. If you have a performance issue, also report it, and we'll try to fix that as well, because that's what we want. I told you, I'm here to encourage people to try it. You know, go home, try your pet project, or try your, I don't know, you're probably not running JDK 10 in production or something, but you know, if you do, hey, flip the switch and see what happens. So please do. And then let me know, this is my Twitter handle, Chris Thallinger. Tweet it out, let me know if it works or not. And that's it. Thank you very much.
We have a bit time to squeeze in a couple questions. Maybe even more than that. So, all right.
Yeah, I have a question, maybe more philosophical, historical.
Ooh, I'm up for that. Should we grab another beer and talk it out?
Maybe.
Okay.
You know, when a new programming language appears, core team has main goal that they should write compiler use their new language. It's like kind of maturity milestone. It's very interesting why for Java is different. Only after 21 years, Java community starts to make some action to have own compiler written on Java.
It's true, but I'm not sure if if I understood you wrong, but the source level compiler Java-C is written in Java for always. That's the main difference. Most languages don't have their own VM or a JIT compiler. Most new languages run on the JVM already, right?
JVM language is kind of, Kotlin, they have own compiler written on Kotlin.
I understand. Yeah. Don't confuse the source level compiler to the native compiler. These are two different things. Java-C is written in Java forever, like since day one. But the JIT compiler that produces the native code, that's something very different. But Kotlin doesn't have that because Kotlin's just using the JVM.
I mean that's Java have compiler, one write on Java,
Right.
one C2 write on C++.
Yes.
And only after 21 years,
Yeah.
we start to write the main part on.
I understand, and I'll answer that question too. I just want to make sure that you understand that the source level compiler is something very different to what I was talking about. Okay, good. The reason why it's happening now is number one, what I was talking about earlier. It's so complicated and we can't train new people, right? 10, 15 years ago, there were people who were still doing C++. Today, not so much. The other reason, and I think more importantly, is you have to have some pieces in place that you can do something like this. And AOT is a very important key point. The problem with AOT compiling Java code is you can do it with Substrate VM, like what Graal VM does. It basically does a closed world analysis of the application. But that's only coming up now, and it's still complicated to do it because Java is so performant because it does runtime optimizations. If Java doesn't have runtime information, what types it's using and which method is hot and invoked a lot, it's very slow if you compile it. You know what I mean? So if we would have done it 15 years ago, it wouldn't have worked. So we needed the time to actually get there. Does that answer your question? It's not very satisfying, I understand, but.
Yeah, I understand it's only after some time we can understand that we need to change it. But we create, create C2 and we have the problem with C2 that it's a big monster and we took in one place and reaction in another different place.
Yeah, but I mean C2 is what, 15 years old now or something? The first 5 it was probably fine, right? And then, you know how old software looks like. It's getting worse and worse and worse. So at some point you have to, switch it out with something new. And that's what we're trying to do, and we're not even there net nearly. It's like, this will take another, depending on you, right? If more people use it, and if we can test it more and get it more mature now, we'll get it sooner. If people don't do it, we'll see. It's in your hands. Was that philosophical enough for you?
Maybe an unrelated question to your work, but is Twitter still happy with Scala?
That I don't know. I really don't know. And the reason I don't know this is I cannot write a single line of Scala code. I don't have to, because everything I see is Java bytecode. So I really don't know. The only thing I know is we're kind of involved in the Scala whatever community they have, and we have some people that are involved in this community. I think so. I don't see a trend towards something else. So, yes.
Especially that's, as you said, Graal's way more efficient compared to Scala than Java.
Exactly. Exactly. More questions? Don't be shy.
Why it's like you made it all why you cut your hair?
Well,
You're from Hawaii.
I know. Well, when you get older.
Yeah, I know.
Okay, good. I'm glad we discussed that philosophical topic.
Apart from that, looks like you made it all so clear. Thank you for that. It was really awesome. That's a bit a little present.
All right.
Us to you.
Thank you very much.
Thank you.